When a packet or a customer arrives at a system, such as a switch or a router, the kind of treatment that it gets is called a service. In this module, we shall understand what is a service in general and in the context of networks. How can we look at how good or bad or average the service is, called the service distribution? Then we'll establish relationship of the Poisson arrival with exponential distribution of service time. The reference chosen is Bertzicus and Gallagher. So what is a service? Service is a set of activities which are performed by the receiving device. It could be either a router. A router performs multiple functionalities such as MAC layer processing, network layer routing table lookups, and actual forwarding of the incoming packet. If it is a layer 2 device such as a switch, the header processing and reference to the port allocation table through which switch decides which port the frame should be forwarded to. If we represent S sub n as the service time of the nth customer, using Poisson arrivals, the customer would have a service time that is exponentially distributed with a mean parameter represented as mu. Since we are talking about service, so mu also represents the service rate. It represents the rate at which the customers are serviced per unit time. So if more customers are getting serviced in lesser time, the service time is small and the service rate is large, and vice versa. This is a good measure to determine if the server or the scheduler is approaching its upper limit. The service times for all the incoming packets are mutually independent. This concept of mutual independence is very relevant and important in terms of network design, because if it were dependent, then more complications would arise. But using the notion of independence, some very simplifying assumptions are made and which help us to get the devices implemented in real world. The inter-arrival times of the packets is also not affecting the service time in any way. That is why, if we were to describe the density function, or how dense would the service times be, how close would they be to each other, is represented by the expression probability that service time for a packet n gets the form mu as the mean and exponent of minus mu times Sn. This is a decaying exponential. What it means is that as the number of customers are more, the service rate is going to be low and the customers are going to experience longer delays. But this does not mean that the customers are going to have the arrival of packets for these customers is going to have any direct relationship with the arrival process of the packets themselves. The service distribution can be represented as follows: 1 minus e to the power minus mu s. This distribution helps us to understand that for a given system, if we are given the average as mu, then what is going to be the overall shape of the distribution for the service. In the context of packet transmission, both the independence of inter-arrival and service times implies that the length of the packet that is getting serviced does not affect the arrival time of the packet which is coming, because the packet which has to come has to come. This particular feature is called the memorylessness. That is, the exponential distribution is memoryless. The service done at the arrival queue of any device is memoryless. What it implies is the additional time needed to complete a customer service in progress is independent of when the service started. Because the service had already started, the server got busy, and it is going to serve the particular packet being serviced rather slowly. But this would have no relationship on when the service was started. It's a very powerful result. And the time up to the next arrival in the queue is again independent of when the previous arrival occurred. It is again the previous concept that the arrivals are independent of each other. The expression of the density function is represented through a decaying exponential that is shown to you here.